This lesson is going to be about number theory. So this first video, I'm just going to be talking about some of the common operators and notations we'll use when we're talking about numbers. And definitely pay attention to this because you'll be leveraging some of this for your proofs for later in the course. So a lot of these are things you might have seen before, and we're just going to work on formalizing them, but some of these might be completely new. The first thing I want to talk about is the floor and the ceiling operator. And basically all that they do is just round your number to the nearest whole number. And the floor or the ceiling is just kind of telling you which way, like which direction you're rounding them. For the floor, you're just rounding down. So you're going to do like the greatest integer less than x. So if x is 2.2, we're going to be finding the greatest whole number less than x, so that would be 2. But for the ceiling operator, you're rounding up, so you're finding basically the smallest integer greater than x. So again, if you have 2.2, the smallest number greater than 2.2 would be 3. I'll give some examples of this, but this is the way you kind of formally define that. So 7.5, the floor of that is going to be 7. The ceiling of 7.5 is going to be 8. So I want to kind of talk about a property that we have of floor, and I think it'll also kind of like help us kind of think about like the different ways we represent numbers. So we have this property of floor that says x minus 1 is less than x, x minus 1 is less than the floor of x. And the floor of x is also going to be less than or equal to the number x itself. Well, the first part of this, the second part of this makes sense, right? Like obviously the floor is going to be less than the number because we're rounding down. So by definition, the floor is going to be less than the number x. But why is x minus 1 always less than the floor? And so let's kind of think about the reasoning behind that. I mean, I think if you think about it, somewhat like just, with an example, it kind of makes sense, right? So if we have like the number 3.4, right? And so the floor of 3.4, so if this is our x, then the floor of 3.4 is going to be 3, right? So sure enough, like if this is x and this is the floor of x, then obviously, 3.4 minus 1 is 2.4. So, sorry, this is a strict less than. So 2.4 is going to be less than our floor, 3, right? And so this is an interesting property, though, that we have. That like this is something that's always going to be true, that if we subtract 1 from x, we'll get this. And so it's, it's basically saying like there's not... there's a difference of less than 1 between this and this is kind of another way of thinking about it. So let's actually prove this though. So this is going to be kind of like the first kind of style of proof. So this is a direct proof. I'm going to do just kind of a more informal version of it. But it kind of it'll help us kind of reason about the way we kind of represent numbers and things like that. So what I want to do is I want to write x as like a different representation. So I want to write it as like y plus d, where like, let me make this a little cleaner, where like y is kind of like the whole number part and d is the decimal part. So again, if I was doing something like 3.4, we could have like y would be 3 and d would be the 0.4, right? So we can always kind of just like separate it into like the whole number part and the decimal part. And if you even have like a whole number like 2, that's fine because y would be 2 and d would just be 0 or 0.0, right? So that's just like your decimal part. And so there's a few things that like we know if we're using this kind of representation, right? So now that we're using this kind of representation, y is essentially just the floor of x, right? So these are kind of things we kind of know just by the definition, like y is going to be equal to the floor of x, because y is, just like that whole number part that we're going to be rounding down to. And so this is something we know. And then we also know that this decimal part is always going to be like a decimal. And since it's going to be like always like less than like the whole number, right? It's like the part that isn't going to be a whole number. We know that d is going to be less than 1, right? D is always going to be some decimal, and it's never going to be 1 or greater. So these are some things we know now based on this definition. If d is a decimal, right, it's because it's going to be something like 0.1 or 0.05 or whatever, but it's always going to have like point something. So d is always going to be less than 1. So these are some properties that we kind of know, and we can use these properties. So I want to use this fact that d is less than 1 and build off of that. So we have this like inequality right here, right? What I'm going to do is so what I'm trying to prove is something about x minus 1, right? And so that's kind of like an indication that probably somewhere I'm going to want to be subtracting 1. A lot of times with proofs, you kind of like, it's just a trial and error kind of thing, like what can I try? But this is kind of something I'm going to play around with. So I'm going to so I'm gonna just subtract both sides by 1. So do -1, -1, and then we get d minus 1 is less than 0, right? So d minus 1 is a negative number. And now I also know that like my x is y plus d. So if I want to kind of make this side look more like x, I know I need to be adding y to it, right? Because I have a d, but I need to add y. So let's go ahead and add y to both sides. So we plus y, and then I get y plus d minus 1 is less than y. And now I can just kind of start plugging some stuff in. So I said x is equal to y plus d, so I can go ahead and substitute this as x minus 1. And I know y is equal to the floor of x, right? I just wrote that right here. So I can just go ahead and plug in on this side the floor of x. And then there is my property. X minus 1 is less than the floor of x. So I get my proof. So again, the square kind of thing is just something we write when we have a proof saying, okay, we're done, we've proved it. And so again, this is kind of a formal because I'm more talking you through my reasoning. So I'll show you later how to kind of be more direct and like more, explicit and like, this is how I got to here. This is how I got to here when you're writing a proof, because, writing a proof is a lot like writing code where, like you want to comment it so that when you go back or if someone else goes back to look at it, they can really understand, what your reasoning was and what you're exactly doing. Okay, so I just went ahead and included this. You can go back. This is kind of just the English like description of what I just went through. And so similarly, the ceiling operator has a similar property where the ceiling is bound by x plus 1 from above, and it's going to be greater than or equal to x. And so I'm not going to prove that. I'm going to leave that to you, but you can kind of, it might be good practice to kind of play around and see if you can prove it similarly, showing like similar to how we did the floor property. Oops. All right. So the next kind of thing I want to talk about is base representation. And so this is just a way you can represent a number using some type of base. And so the base is going to be like some other type of number. So the base is going to be some number that you're going to kind of use to represent your larger number. So what I mean by that is I think the most common type of base representation you're used to is base 10. And so like that's just kind of, you take the digit, like, so I have this number, right? 10,475. And I just take each digit and I can kind of represent each piece of that number times like some exponent really of 10, right? So in other words, I can take like this first digit, this 1 is really a 10,000, right? So I have 1 times 10,000. This 0 is really like 0 times 1,000. So here's 0 times 1,000. This 4 is really a 400, right? So that's 4 times 100. This 7 is really a 7 times 10 because it's a 70. So I put that there. And then 5 is just a 5. So it's just 5 times 1. And I can write all these in terms of exponents of 10. So I can write 10,000 as 10 to the 4th. I can write 1,000 as 10 to the 3rd. I can write 100 as 10 squared. And I can write 10 as 10 to the power of 1. And I can write the number 1 as 10 to the power of 0. Because remember, just any number to the power of 0, so just like x to the power of 0 is always going to be 1. Any number to the power of 0 is going to be 1. So this is just kind of showing how this is the same number as what I have up here, but I'm representing it a different way, and representing it in base 10. And so what that means is it's just like these numbers right here that I'm doing, like putting 2 different exponents. These are all 10, right? It's all 10 to different exponents. And so that's why like we kind of talk about the numbers that we see, like numbers we typically work with, we say they're in base 10 because we look at them just as like these digits in front of our 10 exponents. But there's other bases. So if I can change this base and then it will change these kind of digits. And so it'll change like that kind of representation. So if I change these digits, like that would be my new representation for a different base. So I'll show you a little better what that means. So we can kind of like just generalize what I was talking about first. So, I did like, we can represent a number in the form of like the digits. So this is what I was kind of talking about before with you have your digits. And here, let me just also include the example so it's a little easier to see. So you have like your digits for like this number 10,475, right? Your digits are like 10475. So here I just wrote like D4 is 1, D3 is 0, D2 is 4, D1 is 7, and D0 is 5. So you kind of like write it where you have like your digits times your base, which is this T here, to different powers. And basically it's going to be like a decreasing power. So again, like we wrote our number here as like 1 times 10 to the 4th, 0 times 10 to the 3rd, 4 times 10 squared, 7 times 10 to the 1, and 5 as 10 to the 0. And also just like another thing you'll notice is that like these digits, right, they're all numbers that are less than 10, right? So like 1, 0, 4, 7, 5, like each digit at each like place in your number is always going to be less than 10, right? So you could have like this number right here is going to be some number between 0 and 9, right? And so each of these, right, it'll be some number between 0 and 9. And so that's kind of a property that you'll see in bases where like it's going to be a number between 0 and like your base minus 1. So here, since our base is 10, right, you have like, let me change this color. You have like it's always between 0 and 10 minus 1, or like between 0 and 9, right? So like each digit is going to be between, each of these is between 0 and 9. And so that's a property you're going to see. So if I did base 4 or something like that, then each number would be between 0 and 3, right? And so like, again, we'll do an example to kind of see what like a different base other than base 10 looks like. But I wanted to like show this like common definition with base 10, since that's like what you're most familiar with. So the other type of base I really want to focus on is base 2. And so another word for base 2 is binary. And so this is something you'll commonly hear about in computer science, which is binary. And so this is like how you could represent a number. Like I'm going to kind of show you how we can take a number that's like in base 10 and get it into binary. And so like the number 22 in base 10 here, this is how it would be represented in binary. And so we'll talk a little bit more about that. But the idea is that, in base 2, all your digits are going to be either 0 or 1. And this is the idea of like bits. So a 0 and a 1, a 0 or 1, that's a bit, and 8 bits is a byte. So that's just like kind of common computer science lingo. And so let's actually talk a little bit more about this example before I go on. And I will mention this later, but I did attach a link to a video that kind of explains like why we chose this type of representation. I say we, like I invented the computer, but like why computer scientists use binary as a type of representation. But so yeah, let's talk a little bit more about like having like a binary representation of the number 22. So basically we're doing the same thing we did last time. And I think this sometimes just takes a little practice, but it's like you have, again, like you have your base to a different exponent at each spot. And then each digit you just put in front of that base. So like this 0 comes in front of here. This 1 comes in front of here. This 1 comes in front of here. This 0 comes in front of here. And this 1 comes in front of here. And then basically all that we're doing in this next step down here is we're just simplifying. So I say take 2 to the 4, and I say, okay, that's 16. And I'm multiplying that by 1. So I have 1 times 16. 2 to the 3 is 8. Multiplying that by 0. 2 to the 2 is 4. Multiplying that by 1. 2 to the 1 is 2. Multiplying that by 1. And 2 to the 0 is 1. And so I'm multiplying that by my digit 0. And then I just pulled that all down, and I'm summing it up. So 1 times 16 is 16, plus 0, plus 1 times 4, which is 4, plus 1 times 2, which is 2, plus 0. So 16 plus 4 is 20, plus 2, which is 22. And so this is my binary representation of the number 22. And remember, 22 is actually like, this is the base 10 representation of 22, right? Because if I wanted to go ahead and just represent 22 in base 10, it's the same thing, right? Where I pull, so I have 1 digit times 10 to the 1 plus some digit times 10 to the 0. And then I just put my 2 in here, and I put this 2 in here. And so again, like 10 to the 0 is 1, so 2 times 1 is 2. And 2 times 10 is 20, and 20 plus 2 is 22. So you think of 22, like, so this is the base 10, because it's the digits of this formula. And then this here is the base 2, or the binary. And so these are the same number. These are equivalent numbers, right? This base 10 representation, or point here maybe, like this base 10 representation and this base 2 representation, like those are the same number. So, it's just 2 different ways of representing the same number based on like what base they are in. So I just kind of want to make those 2 differences really clear, because in your lesson on Gradescope, you'll see you're going to be kind of practicing more with translating between binary and base 10. So now I want to talk about how like the length of representing a number in binary, because I just want to kind of like think about this for a second. So it is kind of weird that we're choosing, like, you might be thinking like, why instead of just saying like 2 2, we're saying like this like long number 1 0 1 1 0, because that is like longer to say, right? And so the reasoning does kind of go back to some theory behind computer science, this idea of like a 1 or a 0, instead of like having like these kind of numbers in base 10. And so, as I said, like in the lesson, you'll see a link to a video that explains the reasoning of why we kind of like use this binary representation at all. So another operator that you'll often see when you're trying to prove things mathematically is this idea of something like dividing something else. And so you often see it with this notation, like you'll see like if you have two numbers, A and B, you might say A divides B, or you'll see this A like bar B, and that's often like a common way to denote something divides something. And basically all that means is that like there exists some number that like that you, if you multiplied A by that number, you would get B. So like another way to think about it is that if you were to divide B by A, you would get a whole number, right? That's like what this is saying. And so that's basically what it means when we say A divides B is like B over A equals M. The reason we don't represent it this way, we represent it more with like multiplication rather than division, is just to account for the case where like M or A might be a 0. So that way you don't end up with like a 0 in your denominator. So like you want to like have that, option for A or M to be a 0. So this is why we use like this multiplication notation rather than this division notation. So some examples, actually I'll just show this first one. So we can say 2 divides 6, or this 2 bar 6 is kind of representation right here. Because you have like 2 times 3 equals 6, or like similarly, like as I said, like you could take 6 divided by 2 and you'd get 3, right? So 2 goes into 6, in other words. But again, I wanted to say like we could account for 0. So say like our B is a 0 and like this is a 0 and this is a 0. I still like want, I want to be able to like represent that. And basically like that can be anything, right? Because A times 0 is going to equal 0 for any A, right? So like if M is 0 and B is 0, A times 0 is going to be 0. So A can be anything. So that basically any number, you can say like any number divides 0. So this is just kind of an interesting property that we get from the way we define divides, is you could say any number divides 0. Another operator that you've probably seen before if you've taken a programming class is this idea of mod. And so a mod is the operator that just basically tells you like the remainder if you're dividing by two numbers. So like common, like if we had 3 divided by 2, right? So 2 goes in once, and the remainder is going to be 1, right? So 3 mod 2 would give you 1, because it's basically the remainder when you divide 3 by 2. And so there's more like formal ways to define this. One way is you can use your like floor operator that we've learned, basically, because like 3 divided by 2 is 1.5, right? And so if we took the floor of that, we would get 1. And so basically like the floor of, for like x mod y, the floor of x divided by y is going to be like the whole number, and then you're multiplying that by y, right? And so your y is 2, and then you're basically taking like the whole number 2 and subtracting it, and you get your this is your x, so this is this number. So you have 3. So 3 minus 2, which gives you 1. So this is like a way you could also like kind of define it, is like you're taking like this whole number and you're subtracting away like the whole number part of the division, and then this just leaves you like the remainder. So this is just a way of like formally defining like that, what that remainder is. And so this is like, yeah, so this is just one way you could kind of formalize remainder using your floor operator. So a common like representation though is that you'll also see, and like this is something that you really want to get comfortable with when you're doing proofs, because it's going to be so common. So if you have like A, or yeah, we'll just do A. So if you have like A equal to x mod y, that basically means that you can write A as y times some number k plus x, right? Because x is just like could be that remainder, right? And so like that's kind of what we're saying here, right? Like if this is my k, then like that could be what we're saying here. So this is like also just another way of like representing a number if we want like using that mod notation. And this is something like very common you'll see, and we'll get more practice with that as well. So let's do some examples of mod just so we get used to this idea of just like calculating the remainder, because that's like really what we're doing here. So 5 mod 2. So the remainder, if you divide 5 by 2, is going to be 1. 4 mod 2, the remainder, if you divide 4 by 2, is going to be 0. -1 mod 2 is going to be 1. And I think so that's kind of interesting, right? And so you could get that by either plugging it into here, but also just think about like, what would my remainder be of like negative, like, I think that's where like this definition comes more in handy, that you can actually apply it to negative numbers. Another way you could think of it is like, well, I'll talk about that more in our the next slide. But there are other ways you could think of it for like this type of representation. But basically, like if I were to just like plug this in, so like -1 mod 2 equals, so we take x, so that's -1 minus the floor of -1 over 2 times y. So that would be 2. And so the floor of -1/2 is just going to be negative. So if you think about it like -1/2 on a number line, right? You have 0 and 1, -1. So -1/2 is right here. So if we're rounding down, we get -1. So we get -1 times 2. And then so -1 times -1 is +1. And then we also have a 2 here. So we're actually adding 2. And I'm just going to bring down my -1. So -1 mod 2 equals -1 plus 2, which is 1. So that's how I get my 1 here as my answer. And you'll notice that like the results of like something mod something, kind of like similar to binary representation, like these results should be between like 0 and like y minus 1. So like see how all of these are either 0 or 1 for mod 2. So like that's not a coincidence. You'll get that kind of result like given if you're doing these kind of mod simplifications. So another way you might see mods talked about is in a congruence. And so this is something that should be probably new to you. And so the basically like the one thing you want to kind of look out for with the congruence is this like the fact that mod is put in parentheses instead of like just having like z mod y. Like this is not the same as the mod y. I mean, it is, but it isn't. And so I'll kind of talk about like how they kind of mean different things. So when you have like these parentheses around it, it's basically like you're talking about like how like the whole now like all of the numbers we're talking about are gonna be like modded by y, basically like they're all in that kind of universe. So if you're saying like x is equivalent to z mod y, you're basically saying like x mod y equals z mod y. So you're kind of like talking about them in the world, like when you have this parenthesis, it's basically like everything is being modded by y. And so that's kind of what it means. So I'll give some examples, and I think that'll help as well. But it's just important to kind of notice that like congruence is different than just like straight equality. And like, this is kind of more like, this is something you simplify out, or this is like just another way of saying like everything is modded by y without actually like doing it. And this is sometimes used like in like theorems and proofs and things like that. So basically, like, since 4 mod 2 is 0 and 6 mod 2 is 0, since they both equal 0 mod 2, you can say 4 is equivalent to 6 mod 2. So that's just this kind of idea of this like equivalence. So yeah, just make sure you're taking note of that that congruency. All right, so another thing you might have seen before is a greatest common divisor. And so that's just the greatest common divisor of two integers would be the largest positive integer that divides both of those numbers. So the greatest common divisor of 8 and 12 is like the biggest number that divides both of these, right? So now that we have like a notation for that, that's kind of cool too, like the biggest number such that that number divides each of these. And so the largest number that goes into both 8 and 12 is 4, so the GCD of 8 and 12 is 4. The GCD of 3 and 6 is 3, because 3 goes into 3 and 3 goes into 6. And the GCD of 4 and 7, there's no number that goes into, that divides both 4 and 7 other than 1, so their GCD is 1. Now, another type of terminology that you'll start hearing is this idea of something being relatively prime or coprime. Means the same thing. So they're interchangeable terms, and that just means that their GCD is 1. So basically, like what the only number that divides both of these is going to be 1. And so get used to that terminology too, of two things being relatively prime or coprime. And it ends up being important because like as we'll see in the next video, like there are certain properties that are true for only like coprime numbers. They're not true for like all pairs of numbers. So it can be something very powerful if like nothing else divides these two. So this is like just some of the common operators and notations we'll be seeing in number theory. In the next video, I'll be talking more about applications of that.